Hello everyone. My name is Arav, and me and Sardeep and I will be presenting our research on machine learning enabled synthetic optimization of acyl bond disconnections. Yeah. So throughout this presentation, we will be discussing the following topics. And yeah, before diving into our machine learning pipeline, it's important to understand why this matters in the broader context of medicinal chemistry. So this slide shows data from 1984 and 2014 on the most frequently used reactions in drug discovery. And over time, we see that amide bond formation and cross-coupling reactions have become even more dominant. So in 2014, over 40% of all medicinal chemistry reactions were either amide couplings or Suzuki couplings, up from just 20% in 1984. And this reinforces why improving the efficiency of these reactions, especially amide couplings, is so critical to accelerating drug development. So here we break down these reaction classes even further into representative mechanisms. On the left, we have acylations, which include esterifications and amide couplings. And in our work, we have focused on amide couplings, where a carboxylic acid and an amine form an amide bond using a coupling agent. So in the center, we have the cross-coupling reactions, such as Buchwald-Hartwig and Suzuki couplings. And on the right, are oxidation and reduction reactions, which are also very prevalent, but not the focus of our current study. To ground this in a real world example, let's take a look at AMG 510, which is a KRAS inhibitor recently developed for cancer treatment. So the synthesis of AMG 510 involves both, as you can see, a Suzuki coupling and an amide coupling, which are precisely the types of transformations we just saw dominate the modern medicinal chemistry.
Okay, so initially our lab tested a wide range of reagents for the KRAS project, but the optimal one wasn't clear initially, making the optimization cost take a lot of time and it made it expensive. Beyond just the reagent choice, factors like temperature and time played a major impact on yield, where when the other conditions were kept relatively the same, but when time and temperature increased, so did the yields. Our lab has actually done similar science in the synthesis of compounds which required the optimization of amide coupling reactions. However, this took 21 chemists, 2.5 years, 450 gallons of solvent, and many failed experiments. In the optimization, after using 26 different conditions via LCMS screening, the optimal condition yielding the highest yield was determined to be condition N.
So, as previously shown, optimizing reactions experimentally would require a trial and error pipeline, which would take hundreds of hours of time per substrate, thousands of dollars on materials spent, and acquiring expensive analytical instruments like LCMS, along with a lot of resources wasted. So, um, given the frequency of how of amide couplings and how much they're conducted in modern medicinal chemistry, this cost, time, and labor would quickly add up and cause inefficient optimization. Oops, yeah. So we call this the canonical approach, or giant high throughput, or utilizing giant high throughput condition screening to receive the best conditions, which, as mentioned previously, takes thousands of dollars, hundreds of hours, and liters of solvent. So our new approach for this is more data-driven, where we utilize raw data collected over hundreds of years of experimental research that is currently being stored in open source databases to train machine learning models that can recognize trends and more efficiently optimize reaction conditions. So In a previous study conducted by our group, which I have provided you the QR code if you would like to access it, we claimed that three-dimensional data was the most optimal to predict NMR shift calculations. And so for our current study, we posed the same or a similar question. Does increasing the dimensionality of our data, specifically to 3 dimensions, make our machine learning models for reaction optimizations in this study perform optimally as well? And many have attempted at answering this question in the past by assessing a wide variety of model architectures. So most report that graph neural networks and graph theory-based methods are limited as they are unable to successfully capture crucial features such as steric hindrance and three-dimensional bond angles. And these features can heavily influence reaction outcomes. So three-dimensional data, on the other hand, can capture these features and along with non-covalent interactions, chirality, and stereochemistry. So, in the previous FNMR study that I mentioned, we explored the effectiveness of multiple different model architectures for this use case, along with multiple levels of dimensionality in our training data to back our claim that three-dimensional data is optimal. And we found that all of our models performed a lot better with two-dimensional data versus one-dimensional data, and that also ensemble methods ensemble architectures performed a lot better, outperformed the rest of the models in their testing sets. So, with all this talk of multidimensional data, it's important to understand how exactly they are encoded in our previous study along with our current study. So as for one-dimensional data, smiles are commonly utilized and they are bulk features and they're one-dimensional strings. And yeah, they tell us about the molecule. And for two-dimensional data, it's Morgan fingerprints and molecular graphs are commonly utilized, which give a lot more topological information and chemical information and provide a lot more features by utilizing counts, bit vectors, node feature vectors, and edge feature vectors. And yeah, as I mentioned before, in our previous study, we found that two-dimensional representations of our data led to a higher accuracy of the prediction of chemical shifts, as you can see in the four graphs below, than one-dimensional representations of our data, which you can see in the graph above, in which all of our data is pretty clumped and nowhere along the perfect accuracy line.
Okay. So while starting this project, some of the challenges we faced trying to make our data usable for machine learning included room temperatures not being listed in the reactions we got. Some compounds had multiple names despite being the same compound, and some reactions just didn't have a yield. Because room temperature varies in different places around the world and the reactions are gathered from scientists from different places around the world, we used a range of temperatures from 15 degrees Celsius to 25 degrees Celsius where the room temperature would lie. For compounds with different names, we used smile strings, which are a way to represent chemical structures in line notation through ASCII characters. And for reactions where a yield wasn't given, we simply dropped them because without actually running the reaction, we can't determine what the yield would likely be. Additionally, the Open Reaction Database or ORD dataset consisted of patent and peer-reviewed literature. So for our project, we weighted peer-reviewed literature yields above patent-reviewed literature yields, as peer-reviewed literature typically goes through a much more rigorous process before it gets published, and it's typically more reliable. Lastly, we found that some compounds which had some difference in structures had no impact on the yield or very minute impact on the yield. So we decided to use features not based on the entire structure itself, but based on the reacting functional group. So our goal was to use substrate-specific identifiers such as molecular weight, smile strings, as previously explained, and LogP values to predict reaction-specific sub-identifiers such as temperature, time, and yield. But for our project, we used yield. We started our data curation from the Open Reaction Database, or ORD, as I previously mentioned, which consisted of 2 million reactions and data points, but we ended up filtering out reactions to get a final data set of 3,800 data points.
We decided to train 13 machine learning model architectures for this task of yield prediction, which include architectures from ensemble models to linear models to neural networks and to kernel-based models as well. Our approach to converting this now standardized open source data into multiple dimensions was to utilize our D-Kit. And we decided to test all of our regression models on 3 different levels of dimensionality. And so shown here, this first scatter plot is our best performing yield prediction model, gradient boosting regression. And we utilize only SMILES, LogP, and molecular weight as our training data for this model. And as you can see, our model did not perform very well, as the prediction scatters are far off from the perfect accuracy line, and our R squared score ended at around 0.57. For our two-dimensional model, we utilized Morgan fingerprints as well in our training data for our yield prediction model. And there was actually a little bit of improvement, but much less than we expected based on the trends that we had observed in our previous study. So the model still had significant inaccuracies and would be suboptimal for wet lab chemists. For our three-dimensional model, we used molecular XYZs. We extracted three-dimensional features such as radius of gyration, moment of inertia, and interatomic distances, which and we also implemented SOAP calculations for our carboxylic acid and amine data, which captures local atomic environments. However, once again, even with this much more descriptive data, we barely saw any improvement and we were stuck at an R squared score of around 0.6. In order to push this model optimization even further, we attempted to implement data segmentation through yield binning. So essentially what this did was it added a level of it added an element of classification to our models by having them first bin yields to low, medium, or high, and then actually predict the actual numerical value. So this improved our models very significantly by boosting the R squared score of our best performing model, gradient boosting regression, to 0.81. However, this success was very, very short-lived, as we found that we could only implement data binning in 4 of our 13 models, which were GBR, random forest, extra trees, and k-nearest neighbors. So what happened was, due to the varying architectures of the other 9 models that we had, data segmentation could only be implemented in an unsupervised fashion, in which we actually told the model whether it would be a low, medium, or high yielding reaction. So we were doing the classification for the model, and then it would predict the actual numerical value. So that is cheating, and therefore we received artificially high R squared values like the 0.92 that's shown on the screen for our elastic net model, and clustered graphs with 3 prominent sections, which are low, medium, and high.
Here's a bar chart of all our model performances for yield prediction. We took our best performing model, which was gradient boosting regressor, like RF previously mentioned, and we ran it against an internally curated dataset from one of our other groups. While the dataset only had 13 data points, we found that GBR predicted which yields would be the highest and lowest, even though, as you can see in the graph, the raw values weren't accurate. And at this point, we realized that yield regression was pretty difficult because the data was noisy. So we decided to switch to a classification task. And rather than raw yield regression, which was shown to not be effective, we changed directions to the classification of amide coupling agents. We took the 4 most common coupling agents in our dataset, which are carbodiimide-based agents, uranium salt-based agents, phosphonium salt agents, along with additives, catalysts, and activators. So to evaluate our classification models, we can't use R-squared because R-squared is a regression metric. So we use the confusion matrix, an ROC curve, and accuracy. So the ROC curve essentially shows the true positive rate, which is the proportion of actual positives identified correctly against the false positive rate, which is the proportion of actual negatives which are identified incorrectly against positives. So they're basically just false alarms. The area under the ROC curve essentially summarizes the model's overall ability to discriminate between the classes, in which case, in here, for our project, we have 4 classes. And as the area under the ROC curve approaches 1, this means models can discriminate against classes perfectly. So yeah, we also use the confusion matrix, which shows the true positives, the false positives, the true negatives, and the false negatives for each class. So because we have 4 classes, 4 times 4 is 16, so that's why the matrix has 16 squares. And it essentially reveals to us what classes the models confuses with others, and it can help to reveal patterns in predictions which accuracy cannot. So these are the results for one of our models when run on a one-dimensional dataset of smiles, two-dimensional dataset consisting of smiles and Morgan fingerprints, and a three-dimensional dataset consisting of smiles, Morgan fingerprints, and three-dimensional features such as pharmacore features, conformer-based features, distances between atoms, and features based on those such as mean and standard deviation of the distances, and partial and gas degree charges. Sorry. We found that as we introduce higher dimensionality into the data which the models were trained and tested on, the accuracy increased, as you can see here, between the 1D, 1D plus 2D, and 1D plus 2D plus 3D runs. So we also found that not only did the accuracy increase, the area under the ROC curve increased as well and got closer to 1, and the confusion matrix also showed better results. Lastly, that was one of our models, which is random forest classifier, but here's the other models we ran, which shows the differences in accuracies for all the models. While we found that some models had larger changes, actually much larger changes in performance compared to other models when introducing higher dimensionality into the data, the trend still holds that the higher dimensionality into the data, the better the model performance is. For our project, we would like to thank our other project members, Abhinav Chalasani, Yuhan Lee, and Nisha Padi. We would like to thank our advisors, Dr. Edward New and Dr. Robert Downing. We would like to thank the new lab, and we would like to thank ASDRP as a whole. Thank you. Any questions?
Let's see, round of applause in house. Ready to go. Go ahead and pick on the audience.
Akshita, do you have a question?
I I was wondering what was like the overall goal of your research paper?
Do you want to answer that, Arav, or?
Yeah, so as we mentioned, our original goal for our research paper was to help optimize the conditions of amide coupling reactions without having to go through that trial and error canonical process that we mentioned. And we aimed to do that through machine learning. So we first tried to task our machine learning models with yield prediction, and then we moved to coupling agent classification. To give you a better understanding of that, all of these amide coupling reactions require a coupling agent to successfully react. And what our models do is that they classify reactions to their optimal coupling agent category so that someone that's actually conducting this reaction, their decision-making process is very narrowed down about what coupling agent they're going to use to receive the optimal yield.
Okay, thank you.
Any other questions? The references slide, sure. We have references through all our slides, so you can see at the bottom.
So it is generally the case in formal research presentations that slides are referenced where necessary and where prior art should be mentioned. It is not conventional to put a big fat list of references at the end. This is not like high school. science fair, whatever.
Any other questions? Yeah, Rohan.
Why did you find that the GBR model was the best for like the first part?
The GBR model was best because the architecture of it's an ensemble-based model. So it would be best at like capturing patterns in like higher dimensional data, and even one-dimensional data, which other models can. And between our ensemble-based models, GBR was actually close to the other ones, such as random forest and extra trees.
Okay,
Uh,
thank you.
okay. Amy, you have a question?
Uh, do you know why the Morgan fingerprints or like the 2D models were only like 2% better when in like previous prior art you studied that you observed that they had like more of an impact?
You mean for the yield prediction?
Yeah, yeah. I didn't remember which slide number it was, but it was
I can go back to that.
yeah, I was like there, I think.
Yeah, it was over
The
right
like
before.
one more slide
What?
after.
No, before this.
No,
It with the yield
Yeah.
prediction.
Yeah, before wait, I think yeah, before this one. Yeah, right
Yeah.
here.
Um, we feel that the R square improved only by a bit because the data was noisy, and regression is very hard to do with models when the data is very noisy because we got it from the open reaction database, and we had to drop a bunch of reactions that had no yields, which if we had the yields, they could have actually improved our model, but we wouldn't know that. So yeah.
Yeah, so in other words, the significance of adding dimensionality to our data isn't reflected as much in our yield prediction regression models, simply because regression is difficult with open source noisy data. But it is very well represented in our classification models. Sardeep, can you go to the last slide?
Sure.
Yeah.
Yeah. So
Yeah, go ahead, Sardeep.
yeah, so for the classification models, the models actually performed way better, and this is because adding more dimensionality reveals more patterns in the data, and when models can grasp these patterns, they can essentially learn what coupling agent would be the best. So yeah, you're basically giving it better training, so it'll perform better, basically.
Thank you so much. That helped clear it up a little bit more. Thank you.
Okay, any other questions?
Okay. Last call for questions. Questions in here? Yeah, so just to add on to what has been said, good job to you two gentlemen. That was phenomenal, crap load of data. The grounding principle for how our lab approaches these sorts of machine learning questions is always tying it back to experimental values and to real phenomena. A lot of if you just go on Google Scholar, you search up like machine learning for whatever. I would say, over 1/3 of those are basically ghost phenomena, artificial correlations that make sense for a limited case-based learning, but don't have any real tie to real-world correlations or causative effects. And so, a good challenge I think, for these two and the others in the project has always been, how do we tie the data that's going into the ML model to represent and reflect physical phenomena that we conduct in the laboratory as molecular scientists? And secondarily, how is the interpretation of the results from different ML algorithms, how is that understood in light of, again, real physical phenomena? So good job. We are moving along to the next presentations.